Hello, well, hello everyone. Good afternoon. Good evening. Welcome to 10th week of the live problem solving session for the course Fundamental of Semiconductor Devices by Professor Digvijay and Nath. I am Mayank Goyal and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. And this course is being taught by Professor Digvijay and Nath, who is an associate professor at ISC Bangalore. The course plan for the week 10 is solar cells, their working principle, efficiency, fill factor, Shockley quasar limit, and different types of solar cells. Then photoreactors, their operation, their figures of merit such as responsivity, quantum efficiency, band gap, directivity, etc. And then examples of IR and UV detectors. So this tutorial session is happening every Sunday 6 p.m. to 8 p.m. on this Google Meet link. So I will show you some I will give you some MCQ questions which will help you get a understanding of the concepts. So first question, what is the primary function of a solar cell? To store electrical energy, to convert sunlight into electrical energy, to amplify electrical signals, to regulate voltage.
B sir, convert sunlight into electric energy.
That is correct. The function of a solar cell is to convert sunlight into electrical energy. So it is a device which when sunlight falls on it, you in response you get electrical signals, not signals. I mean basically it creates a poten- potential which it creates charge which can be stored and then can be used later. Which term describes the basic mechanism behind solar cell operation? Thermal conduction, magnetic induction, photovoltaic action, electromagnetic interference.
Sir, option C sir, photovoltaic action.
That is correct. A solar cell is basically solar cell operation is a photovoltaic action. So a photovoltaic means I insert photons and output is some voltage. That is called photovoltaic action. What is the approximate temperature of the sun as a black body radiator? 4800 K, 5300 K, 5800 K, 6300 K.
Sir, option C sir, 5800.
That is correct. 5800 K. So a solar cell is you have been reading since this childhood. The temperature of the surface of solar cell is around 5500 degrees Celsius, which is around 5800 Kelvin. Why is silicon commonly used in solar cells? It has the highest efficiency among all semiconductors. It has the lowest production cost. It has the widest bandgap. It is easy to integrate, cost effective, and compatible with existing electronics.
Sir, 4 sir.
That is correct. So, so like before solar cell existed, we were using silicon for other electronics. So, all the processes for silicon cells already existed. So it became the automatic choice. And also the band gap of silicon is like considerably good for solar cells. In a PN junction solar cell, where are photon gathered source electrons converted into electricity? In the P type region, in the N type region, in the depletion region, in the metal contacts.
At depletion region.
That is correct. So the carriers that are generated in the depletion region are best to convert to electricity because there's a built-in electric field in the depletion region which helps us separate, keeps the electrons and holes that are generated separated. What happens to electron hole pairs generated in the neutral regions? They contribute to electricity generation. They are swept away by the electric field. They recombine and don't contribute to current. They enhance the cell's efficiency.
Sir, they are swept away by the electric field, sir.
That is wrong. The correct answer is they recombine and don't contribute to current. So if you are generating an electron hole pair in the p type or n type region where there's no electric field, so what will happen is they will immediately recombine and they won't be able we won't be able to collect them at the edges.
Sir, can you repeat, sir, one more time?
So there, if you take a p-n junction, there are basically three regions in there: p-type region, depletion region, and n-type region, right?
Yes, sir.
So in the depletion region, there's a built-in electric field, but
Okay, sir.
the p-type region and n-type region, they're the they're the charge they have the charge neutrality. They are following the charge neutrality. There's no built-in electric field there. So when you generate an electron hole pair in those p-type or n-type region, so there's no electric field to separate the carriers. So they will just recombine, and they and due to and when they recombine, so we don't have free electrons and holes. But if but if an electron hole pair is generated in the depletion region, so what the free electric field will do, it will throw electrons on one side and holes to the other side. So electron will go to the p-type region and hole will go to the n-type region. And so now the p-type region now has an extra electron. So that now that extra electron, it can't absorb that electron because there's no available hole for it to absorb. So that will just go to the edge of the p-type region and it will go out. Similarly, hole will go out on the other end, and that is how we can collect electron and hole, and that's how we will get a electric current.
Sir, so, sir, can I ask you one question, sir?
Yes.
So, sir, the main role of the p-type and n-type region is to recombine the electron and hole, and it can generate extra electron and hole which can move to the depletion region to conduct current. Is this correct, sir?
You can say that, but see, you want a depletion region. How will you form a depletion region? To get you want you want light to fall on your sample, and then it will generate your electron and hole pairs, right?
Yes, sir.
But they are only going to contribute to your current when they are collected at the edges.
Okay.
So you want to generate the electrons and holes, and then you want to separate them so that they move to one edge and the other edge. Electrons to one edge and the holes to other edge. So to do that you need a depletion region. And how will you form a depletion region?
Depletion region formed due to the different type of carrier we can sandwich.
Yeah, so you need a p-n junction to form a depletion region.
Yes, sir. Yes, sir.
So that is why we want our depletion region to be maximum. We don't want that much of p-type region and n-type region. because
What, sir?
we want our p-type region and n-type region to be minimum, the size of p-type region and n-type region to be minimum, and our
Yes, yes, sir.
depletion region to be maximum.
Sir, please move to the previous question, sir.
Yes.
Okay, sir.
Yeah. So what will happen is, if I generate an electron and hole here, they won't go, they will stay here because there's no electric field here. But see, there's an electric field here like this, right? This region has an electric field, built-in electric field, right? So if I generate an electron and hole here, my electron will go this side and my hole will go this side. And when it goes here, so there's a diffusion length involved here. There's a diffusion length here. So like this is called the diffusion length. So if I if my so when electron is traveling through here, it is going to diffuse in the p-type region, right?
Yes, sir.
But there's a diffusion length after which it will get diffused. So if I make my p-type region shorter than the diffusion length, then it will cross to this edge and it will get collected here. Similarly, for n-type, I will, for hole in the n-type region, I will have some diffusion length. If I make my make my n-type region smaller than the diffusion region, I will have my hole reaching this edge. And when I get an electron at this edge and a hole at this edge, then I have electric current, flow of current.
So, sir, there is any relation between the deflection width and p-type n-type region. That that deflection width must be lower than your n-type. Deflection width must be lower than n-type region or p-type region.
No, so the see your depletion width is dependent on your this thing like doping. How much your
Doping.
n-type and p-type regions are doped. That is your depletion region. But your your depletion region cannot be your whole n-type region, or your whole p-type region cannot be depletion region, because then you will have breakdown.
Okay, sir. No, sir. I just want to know that is there a relation between that I have to means fix the my n-type region in suppose 1 micrometer, then depletion width will be 0.5. Is there any relation? Is there?
No, relation is not like this. Your depletion region width is determined by your doping.
Doping. Yes, sir.
So
No,
if
sir. You
if,
tell me.
if
You
for
tell
certain
that.
if for certain doping, my depletion width is like 1 micron, even if so there is something called a short channel and a long channel, short diode and a long diode.
Yes, sir. Yes, sir.
So typically the calculations are done for a long diode model where your channel channel length is much larger than your depletion region width. Diode the and p-type and n-type regions are much larger than your depletion region. So for short diodes, calculations change slightly. So typically your depletion region is always smaller than your p-type n-type regions.
Okay, sir.
Why is the top layer of a solar cell made very thin? To reduce manufacturing costs, to increase mechanical strength, to prevent photon absorption waste in the top layer, to improve thermal conductivity.
Sir, option D, sir.
That is correct. That is wrong. The answer would be to prevent photon absorption waste in the top layer. So, so a solar cell, the light will fall from the top only, right?
Yes, sir.
So, what is the first layer that it will see? It will be the p-type or the n-type layer, right?
Yes, sir. Yes, sir.
And if you are doing light absorption in your p-type or n-type layer, it is a waste because it is not contributing to your current. So you want
Okay.
most of your light to fall in the depletion region.
Okay.
So you want your thickness to be thickness of your top layer to be less, so that it your there is less absorption in the way, less absorption in that layer, and most of the absorption is then in the depletion layer.
Okay, sir.
What is the main disadvantage of using a very narrow bandgap semiconductor for solar cells? Higher production cost, lower open circuit voltage, increased resistance, poor absorption.
Sir, should I guess, sir?
What?
Should I guess something?
Okay, guess.
Sir, it can create lower open circuit voltage, sir.
That is correct. So you know what is open circuit voltage?
Yes, sir. Yes, sir.
What is it?
Sir, actually, open circuit, there are four important parameters. So there are VOC, JSC, fill factor, and efficiency. So open circuit voltage means, sir, when the we can initially start the circuit, the maximum there will be a relation between V and I graph, sir. So when current is zero, the maximum voltage can be applied by circuit is called open circuit voltage, I think.
So that is true. Like basically your circuit is open, no load is attached to your circuit. It means basically that. Or there's an infinite resistance attached to your circuit, so that there is no current flow. So basically it is basically what open circuit voltage basically means, basically how much maximum amount of voltage your solar cell can generate.
Okay, sir. Okay.
So so what is basically or solar cell? It is taking in sunlight, right? What is the sunlight spectrum?
Spectrum divided into three parts, sir. IR, answer visible light, and UV.
Yes. So and how is your photon absorption related to your band gap?
Uh, Sir, photon absorption HC by lambda. Energy equal to HC by lambda. So lambda equal to HC by energy.
Uh, if I have a band gap of 1.5 eV, let's say 2 eV. If I have band gap of 2 eV, can I absorb IR radiation?
No, sir. Actually, I think 1.1 to 1.4 is in the visible range.
The visible range is around 1.8 eV. Yeah, above 1.8 eV is visible range.
Okay, then, sir, below is IR, sir. Below is IR. 2 is a visible range.
Yeah, but if my my band gap is 2 eV, can I absorb, and I am throwing IR light on my material, will it absorb?
No, sir.
So all my solar sunlight that is below 2 eV is waste, right?
Yes, sir.
So I can just go a very small band gap like 0.1 ev, 0.2 ev, then it will absorb everything, right?
Yes, sir. Up to 1.8, sir.
Why up to 1.8?
No, no, sir. Actually, I say that you say that 1.8 is the maximum range for IR. Beyond that, there will be visible range.
Yeah, but sunlight is UV, visible, IR, everything, right?
Yes, sir. Sunlight spectrum is everything.
Yeah, so if I go very low band gap like 0.2 ev, 0.3 ev, then it
So
will.
then all the range will be accepted.
Yes, so but there is a problem here that I am getting very low open circuit voltage for this band gap.
Yes, sir.
Why do you think that is?
Because sir, if you apply some point one, point two, uh, point to your EV band gap, so for a very little energy of photon, every start conducting, sir. Huge current is there.
Yeah, but we want maximum current and maximum voltage, right?
So sir, voltage will be minimum, na. If the maximum current will flow, sir, then the open circuit voltage will be minimum, na.
No, you can have both high, both increase. You want to both of them to be good.
Yes, sir. I want both of these good, sir. But if we make the band gap is very lower, then for a means if sunlight will fall on the solar cell, there will be huge current flow through the device.
Yeah, what is the problem in that?
Sir, I think open circuit voltage will be lower, sir.
No, but that will increase. How is that that is how is that affecting my voltage if my current is high?
Sir, if current is high, sir, if your load will be very low value resistance to maintain that.
No, but I am talking about open circuit voltage. There is no load here. There is no current
Okay,
flow
okay,
here.
okay. So, open circuit. Okay, sir. Okay. Now I explain a little bit. Try to explain, sir. Sir,
Okay.
you told that if your band gap is very low and you apply as, as put on in the that particular device, then sir, I think open circuit voltage have not got a very. I have no idea, sir. Please tell me, sir.
Okay.
I,
Like I will. So your band gap is, let's say, 1 eV, and your photon. I am throwing photons of 2 eV on my sample. Okay. What will happen? Hello.
yes, sir.
So my band gap is 1 eV, and I am throwing photons of 2 eV.
Band gap is 1 eV, and you throw
Photons of 2 eV.
photons of 2 eV.
Yeah. What will happen then?
Band gap is 1 eV. Band gap is 1 eV, and you throw photon of 2 eV. 2 eV. Then, sir, I think, sir, then there is, sir, recombination is there, sir. Radiative recombination. I think
How?
because, sir, electron from the valence band jump to the more higher than conduction band, and then it can be again relax and back to the uh, top level of bottom level of the conduction band. So there will be a radiative recombination is there.
That is neither radiative nor recombination. You are correct. What you are saying correct, but it is first of all it won't be radiative. Second of all, it's not recombination.
Okay.
So radiative means that you are releasing photons. You are
Oh,
releasing
okay, okay, no,
radiation.
sir. Yes, sir. Yes, sir. So
It
there will
is
be
non-radiative
a non-radiative recombination. Sorry, non-radiative recombination.
and it is not recombination because electron is going back to your top of the conduction band. It is not recombining with the whole. So
Okay,
it is just losing energy in a non-radiative way.
okay, sir.
So that energy is lost to heat.
Yes, sir. Yes, sir.
Yeah. So if we so going a very narrow band gap is also not good, and going a very high band gap is also not good, because then you are missing out on most of your sunlight.
Yes, sir. Yes, sir. I got to understand, sir.
What is the primary advantage of multi-junction solar cells? Lower cost, simpler design, better absorption across different wavelengths, easier manufacturing.
It is quite obvious, sir. It is C, sir. Better absorption across different lengths, sir.
Yes, so like just now, like I said, so like take silicon 1.1 EV. So if you are throwing so your most of your light is around two, let's say 2 EV. Most of our sunlight is 2 EV, but our silicon band gap is 1.1 EV. So all that extra energy is waste now, right?
Yes, sir.
So now if I put another semiconductor along with silicon, I put another semiconductor that absorbs in that has a band gap of 2 EV. So now everything below 2 EV, I have silicon still absorbing below every energy below 2 EV. Between 1.1 to 2 EV, silicon is absorbing, and above 2 EV, I have both silicon and this another material absorbing, but the silicon is outputting a 1.1 EV electrons. This material is outputting 2 EV electrons.
Sir, one more time. Last sentence will be recap, sir.
Yeah, so silicon, it is absorbing everything below 1.1 EV, right? Everything above 1.1 EV, silicon is absorbing, right?
Okay.
And but if I let's say if I'm my solar spectrum is peaking around 2 EV, but
Okay.
that extra energy between 1.1 EV and 2 EV is getting wasted.
But sir, I have just asked you one extra question, sir.
Yes.
If I make multi junction, so we have to make a different layers are there. So is there any defects, more interface defect will be created compared to single junction?
There will be, that is the thing, right? We have to optimize.
Okay, okay, sir. Okay.
That is the thing, right? That, see, uh, if there were no, if there were only positives, no negatives, then why are we not doing multi junctions, right?
No, no, sir. I just I know that, sir. There is already some negatives are there, but I just want to know that is the multi-junction as means one advantage. Whatever you tell that if I have applied two EV energy of photon, then all the spectrum will be absorbed. Yeah, okay, sir. But sir, is there any drawbacks are there?
Yeah, there are drawbacks, right? Because you are growing another material on top of silicon, then there will be defects created in that top material. Like last week we studied epitaxy, right?
Effects, yes, sir.
So there will be lattice mismatch effects, other epitaxial effects, defects.
Yes, sir. Yes.
So all those issues are there between for heterojunction. It basically you are creating a heterojunction there, right?
Yes, sir. Yes, sir.
It's a
Multi-junction is also called heterojunction, sir.
heteroepitaxy you are doing. So that will create issues. The short circuit current ISC in a solar cell is measured when the cell is reverse biased, the voltage across the cell is zero, the cell is forward biased, no light is incident on the cell.
Sir, it is voltage across the cell is zero.
That is correct. Solar cell is short circuit current is measured when by keeping voltage across the cell is as zero, basically at that point current current your current generated is maximum. So ISC is the maximum amount of current that can be generated by your solar cell. The open circuit voltage is measured when maximum current flows, no current flows, maximum power is delivered, the cell is short circuited.
Maximum current flow.
Wrong. It's no current flow. We just talked about it.
Oh, sorry.
So VOC is the maximum voltage that your solar cell is giving out, and ISC is the maximum current that your solar cell is giving out. So you want your both of them to be maximum. You want maximum VOC, maximum ISC, but that is not possible. What is the Shockley-Queisser limit primarily concerned with? The theoretical maximum efficiency of multi-junction solar cells, theoretical maximum efficiency of single junction solar cells, minimum band gap required for solar cell operation, maximum current density possible in solar cells.
Sir, I think theoretically maximum efficiency of single junction solar cell.
That is correct. So Shockley-Queisser limit gives the theoretical maximum energy efficiency of single junction solar cells. So do you know the Shockley-Queisser limit for silicon solar cells?
At 33%, I think.
That is correct. For silicon, the shock basic shock according to Shockley-Queisser limit, you cannot, if you are using a silicon solar cell and you make the perfect silicon solar cell, still your efficiency cannot be more than 33% because of because primarily because your silicon band gap is 1.1 eV and your solar spectrum peak is peaking around 2 eV. So all that extra energy is getting lost, mainly because of that your efficiency is reducing. And but right now, like the maximum efficiency that we have got is for a silicon solar cell is around 25 to 27%, and in industry it's around 20%, 17 to 20%.
So that theoretically 27%.
Not theoretical, like in research solar, in, in research the maximum that we have got is 25 to 27%. Limit is 33%, but we have got 25 to 27% in research, and the one that you buy in the market, they have around 17 18 to 20 17 to 20% efficiency. For silicon solar cells, what is the typical open circuit voltage achieved compared to its band gap? 100% of the band gap, 90% of the band gap, 70-80% of the band gap, 50% of the band gap.
Uh, I think it is 90% because 70 to 80% or 90%. In between that.
So it is 70 to 80%, so around 75 to 78% typically you get. So like how much would be 70-80% of 75% of 1.1?
It will be near about 0.8.
Yeah, so typically the open circuit voltage you get for a silicon solar cell will be around 0.8, 0.85, around that. Which factor determines the optimal band gap for maximum solar cell efficiency? Only the short circuit current, only the open circuit voltage, the trade-off between short circuit current and open circuit voltage, the fill factor alone.
The trade-off between short circuit current and open circuit voltage.
That is correct. So if you go a very low band gap, you will have your open circuit voltage will reduce. If you go a very high band gap, your short circuit current will reduce, because then you are losing out on the solar spectrum. So there should be a trade-off between your solar short circuit current and open circuit voltage, so that your efficiency efficiency gets maximized, and that is around 1.3 to 1.5 EV. So your optimal band gap for a solar cell should be 1.3 to 1.5 EV.
Sir, last sentence, sir. What is it? 1 point.
1.3 to 1.5 EV. That should be your optimal band gap for a single junction solar cell. What is the fill factor FF in solar cells? The ratio of total solar power to electrical power output, the ratio of actual power output to the product of VOC into and VIC, the ratio of short circuit current to open circuit voltage, the ratio of input power to output power.
Sir, it will be option B, sir. But I have to ask you a question, sir.
Yes, the answer would be
B,
actual
B, sir.
power output to product of VOC and ISC. Ask.
Sir, in last case, sir, in last question, you told that the max optimal band gap for silicon means for single junction is 1.3. Is this is composite material?
No, single junction, right? Single junction. There's only
No, no,
one
no.
material.
Actually, if I take, sir, one material such silicon, germanium, or any kind of material, sir, gallium arsenide.
Yeah, it's any so obviously for every material the band gap is different, right?
Yes, sir. But 1.3 is the maximum band gap for single junction. That sentence you have told, na?
Not maximum band gap, optimal band gap. Best
Okay,
band
okay.
gap. Best band gap you will should have for your to have maximum efficiency. Like if you're going band gap, so one material you can have band gap of 0.8 EV, then silicon 1.1 EV, then for gallium nitride you have 3.4 EV, right?
Yes, sir. Yes, sir.
So, but what is the band gap that will give you maximum efficiency? Let's say maximum Shockley Quasar limit.
Okay.
So
So, sir,
for silicon it is 33%. Like for 1.1 EV, 1.1 EV your limit can go to 33%, let's say. Then for, let's say if I'm going 1.4 EV, my maximum limit can maybe goes up to 45%.
sir, if the band gap is increased, sir, the percentage is fixed, 33%.
No,
No, no, no. I just want to say that in Shockley Quasar limit, there will be a maximum percentage there, which can depend upon band gap.
it depends upon band gap and also material properties also.
Okay, okay, okay. Sir, is there
Shockley
any
Quasar limit does not
means
depend
particular
only,
equation?
it depends also on material properties also. Like,
Is there a particular equation is there, sir?
I don't know if there's any equation.
Okay, 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 sir. Okay. No, actually, sir, you told that if 1.4 is there, EV, then it will be 40%, 45%. So I think there will be a
No,
means.
I was just giving an example. I'm not saying that for 1.4 it is 45%.
But sir, I find in a different context, sir, that if the band gap is, let's say, one means, sir, third generation solar cell, perovskite solar cell,
Hmm.
if the band gap is tuning, whatever you told that 1.3 to 1.4, the efficiency Shockley Quasar limit will be changed, sir.
Yes.
if the band gap is tuned possible, then I think, sir, it can be, sir, Shockley quasar limit will be varied.
Yeah, it will vary.
So I think there will be some relationship. I don't know. I just ask you, sir, if there any relationship is there or not.
There would be a relationship which between band gap, because your efficiency is dependent on band gap also, right?
Yes, sir. Yes, sir.
So see the when this limit perovskite was not in the picture when this limit was given, the Stokely quasar limit was given.
Yes, sir. Yes, sir. Yes. Sir.
So that time band gap tuning was not a thing. If you have a material, it has a fixed band gap.
Okay. Okay.
If you are using silicon, your band gap is fixed. If you are using germanium, your band gap is fixed.
Yes, sir.
So they didn't think that at that time about band gap tuning.
Okay, sir. Okay.
So fill factor is the ratio of your power output to the product of VOC and ISC. So so let so we for a solar cell we got VOC and ISC. So the maximum possible voltage and the maximum possible current. But
What, sir?
so we made a solar cell. We calculated VOC and ISC for it, the maximum possible voltage and the maximum possible current.
Okay.
But but they are the VOC is calculated with zero current and ISC is calculated at zero voltage. But but basically at both of them the power is zero. So for some lower voltage and for some lower current, I will have my maximum power. I won't have my maximum. I I won't be see like if I so this is V and this is I. So this is my VOC and this is my ISC. So what is theoretically the maximum power output I can get with this solar cell?
Sir, there is sir, rectangle is there. Rectangle.
Yeah. So at this point is my VOC into the power output at this point will be VOC into ISC, right?
Yes, sir.
At this, so this is the theoretically maximum power output I can get for this solar cell. But what actually happens is I get something like this. I get something like this. So here the maximum power output I will get at this point at some reduced VOC and VSC. At this is my V P max and this is my I P max. So this is so so fill factor is basically how much of this rectangle you have filled. That is by this rectangle, right? This smaller rectangle is what you can max fill. That is my fill factor.
So, sir, ratio between the inner rectangle by to the outer rectangle is your fill factor, na?
Yeah, that is what.
Yes, sir. Yes. So maximum fill factor will be maximum will be 80 to again 70 to 80%, na?
Yeah, fill factor is generally around 70-80%.
Okay, sir. Okay.
Which material has the band gap closest to the optimal value for single junction solar cell efficiency? Silicon, germanium, gallium arsenide, gallium nitride.
Sir, obviously highest will be the answer, sir. Gallium nitride.
Are you sure?
No, sir. Actually, gallium nitride, you in your last class say that it is used as a buffer, sir.
What is the question? What?
Band gap closest to the optimal value for single junction solar cell. Silicon, sir. Silicon.
You sure? Look at the options and look at what, and remember what we just talked about.
Sir, you told that if the band gap is more, it will be efficiency will be more.
What is the optimal band gap value I told?
1.3. So 1.42 gallium arsenide is the.
Yes, so gallium arsenide is the answer. So optimal band gap is 1.3 to 1.5 around.
Yes, sir. Yes, sir. Okay, okay, sir. 1 minute, sir. So, sir, means sir, if the band gap is around 1.3 to 1.5, that will be the highest efficiency for single junction solar cell.
Yes.
Okay, sir.
It also, the efficiency also depends on other material properties like your your absorption coefficient, quantum efficiency of your material, and other things.
Sir, like sir, your another property is that doping, your NAND value.
Yeah, that I am getting the best option, whatever the best option is there, because that is in my control, right? Doping is in my control,
Yes, sir.
but quantum efficiency is not in my control.
Yes, sir.
Would you know what is quantum efficiency?
Yes, sir. It is a material property, sir.
Yeah, but what is quantum efficiency?
Now, sir, I don't know. Actually, I cannot explain, sir. Now I cannot. Quantum efficiency means sir highest efficiency
No,
for a optimal condition.
no, quantum efficiency is different term. Quantum efficiency means, so if I'm if my if my sample is, let's say, absorbing 10 photons, like there are 10 photons falling on my sample, and I am generating 10 electron hole pairs, then my quantum efficiency is 100%. But for 10 electron hole pairs, I am only able to generate 5 electron. For 10 photons, I am only able to generate 5 electron hole pairs. Then my quantum efficiency is 50%.
Okay, sir. Okay.
And that is a material property. So, which is why I will talk this question. What is the primary advantage of perovskite solar cells? Lower cost, better stability, rapid efficiency improvement in research, simpler manufacturing process.
Sir, it can answer means sir simple manufacturing process as well as lower cost, sir. Because sir, I
Both
think
of them are wrong. So, the, because the manufacturing process is definitely not simple for perovskites.
but sir, it is it. I heard that sir, it does not require any kind of high heating process like silicon. So it is means sir lower cost is there, sir. Because sir, it can be generated in the lab by I don't have the idea the industry, but I have stability is very poor, sir. I don't know that. And sir, second thing is that it can be generated by the only just layer by layer spinning technique. I heard that.
Yes, but there is something called yield. Yield. You know what is yield? Yield
What's
is
that?
yield. Yield.
Yield, yield. Yield.
Yes.
No, sir, I don't know the meaning, sir.
Yield means what is the output out required out what is the out, so desired out so you have a desired property, right? What is the so you let's say you take the precursors, you take the basic material, and your so I am inputting my basic material to get 10 kg of output.
Okay.
but 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 there is some losses in the process. Then there is some then there is like the output is not of desired quantity, desired not does not have desired properties, so it discards those output. So the desired output that I am getting is only 5 kg. So that is 50% yield. Let's say, uh, how can I explain? Let's say you are making some food. You
Okay, sir.
you are making sabji, let's say, but and the ingredients that you took, that is for 5 kg of sabji. Okay,
Okay,
like
sir.
you take 2 kg 3 kg potatoes, 2 kg onion. So the output you are expecting is for 5 kg. But what happened is, like, when you were boiling your potatoes, you saw your one potato fell on the ground. So now you have to throw that potato. Then your your some sabji got stuck to your pan. So that also you have to remove. Then then you are making your sabji in 3 batches. In one batch, your you put extra salt, so you have to throw that batch also. You can't serve that batch to your customers. So now only 2 batches remain. So now the output that you get is only 2 kgs of sabji. You wanted to make 5 kg of sabji, but you are only left with 2 kg of sabji. So that
What,
was
sir?
so you started with material for 5 kg of sabji, but in the end you only made 2 kg of sabji.
Yes, sir.
So that is a 33% yield. Your
Yes,
yield
sir.
here is 33%, not 33%, 40%. Sorry, your yield,
Five, 2 by 5.
yeah, 2 by 5. So yield is 40%. So for perovskites, the yield is very less right now because the processes are not optimized. So so that increases the cost. To lower cost, you want maximum yield. That increases the cost. So you can say that the manufacturing process is simpler, but not very simple also, because getting the right properties is not easy.
Yes, sir. Yes, sir.
Yes. But one of the primary benefits of perovskites is the high quantum efficiency. So there are basically there are almost no defects in your band gap. In our perovskite band gap, there are no defects. So almost all the incoming photons result in electron hole pairs because there's no trapping. So their quantum efficiency is almost 100%. That is one of the primary benefits of using perovskites.
Okay, sir.
So what is the key difference between solar cells and photoreactors in terms of their primary function? Solar cells operate at higher voltages. Photoreactors are only used for UV light. Solar cells are designed for power generation while photoreactors are for sensing light. Photoreactors can only work with visible light.
Sir, C, sir.
That is correct. So so basically a solar cell and photodetector, if you see, they look they are very similar in structure. Both are basically a type of junction. PN junction, Schottky junction, heterojunction. Both of them are junctions only with a depletion region. Both of them work the same way. You throw light, you generate electron hole pairs. But the difference comes in their functionality. In a solar cell, you want the electron hole pairs to give a power output, while in photo detectors, you you want your electron hole pairs to give a change in your signal, so that you can know that there is a light falling on your sample.
Sir, is there any other device on the, like, sir,
What?
uh, like, sir, IV curve will be same, sir, photogen.
IV curve is basically the same, but that's the thing. Yeah. IV curve is how you are calculating the IV curve, right? For
Yes,
the
sir.
solar cell, the IV curve means a different thing. There you are there you are in solar cell, the you are calculating the IV as a output. In photodetectors or LEDs, the IV curve is an input. Basically, you are giving an input power, and you are calculating you are giving an voltage input, and you are calculating how much the current is changing. That is your IV curve. But in solar cell, you are calculating the output. What is the output power? So that is why we say that a solar cell operates in the fourth quadrant. Your LED operates in your first quadrant.
Why, sir? Why, sir?
So this is your first quadrant, second quadrant, third quadrant, fourth quadrant. This is V, this is I. So for a PN junction, this is how the IV curve looks, right? This is how the IV curve looks. But for a solar cell, the IV curve is generally drawn like this, because there you are talking about output power. Here you are giving in power as an input. Here the power is output. So we and then what we do is we shift this up above, and we draw it like this. This part, this fourth quadrant, we shift it to the first quadrant, and we draw it like this by calculating the how much maximum current we are able to get.
Sir, basically, sir, ask a question, sir.
Yes.
Basically, sir, whatever you told, that photo detector can be act as a opposite to the solar cell. That photo detector input will be your voltage, output will be light.
Uh, that is not what I am saying. There is the light photodetector is not outputting light. Both of them are. That is what I am saying. Both of them are fundamentally the same things. They are both a PN. They are both a type of PN junction, and in
Yes,
both
sir.
cases, you are shining light, and you are generating electron hole pairs.
Okay, sir.
But the you are how basically the differentiation comes in the functionality. In a solar cell, you expect that electron hole pairs to generate power output.
Okay.
And photoreactors, you expect that electron hole pairs to change your current signal. So you already have some current flowing through a photoreactor, and your power, the light that is generating electron hole pairs is increasing your current.
Okay, okay. So, sir, as per your concept, the current which will already get will be changed by the light.
Yes, that is how you base that change in current tells you that there is a light shining on your photoreactor. For a photoreactor with 100% external quantum efficiency, how do responsivity change vary with wavelength? Decrease linearly with wavelength, increase linearly with wavelength, remain constant regardless of wavelength, varies exponentially with wavelength.
Constant, sir.
So it's actually increases with wavelength. So higher the wavelength, your responsivity will be higher. So responsivity is basically the change in output current versus your input photon power. So if my input power, the light that I'm if I'm shining 2 watt of light, the power of my light is 2 watts, and my the change in current that I'm observing is 2 amperes. Then my responsivity will be 2 amperes by 2 watt, 1 ampere per watt.
Sir, I cannot get, sir.
So responsivity is basically given by delta I divided by P in. So this is the photon power that the light power that you are shining on your sample, and this is the change in current that you are observing. So if you are shining a light of 500 nanometers, and if you are shining a light of 1000 nanometers with the same power,
Yes, sir.
the power is same.
Okay.
So wait, uh,
So, sir, thousands will be
so the
less
thousand,
responsibility. Less responsibility.
yes, so the thousand nanometer will give you the responsivity will be higher. The change in current will be higher for 1000 nanometers. 1000 nanometers. So
Sir, you told that 500 and 1000, na?
hmm, what?
Sir, power in the denominator part, na?
Yes.
So, if the power is increased, sir, responsibility will decrease.
No, no. Your responsivity is your power. If you increase your power, your current change will also increase. So I am not changing my power. I am changing the wavelength and keeping the power same.
Okay, okay. You change the wavelength.
Yes.
So, power change is less compared to current change.
Yes. So no, no. You are getting it wrong. So I am shining two light. In one case, my wavelength is 500 nanometers. In another case, my wavelength is 1000 nanometers.
Okay.
And my power is same in both cases. How will my delta I will change?
Okay, okay. Then, sir, I think if lambda will be changed. So sir, energy will be high for higher value of lambda. So sorry, energy will be high for lower value of lambda. So the current will be changed.
Yeah, current is changing in both cases. So let's say here my current is delta I1 and here is my current is delta I2. What is the relationship between delta I1 and delta I2?
Then obviously delta I1 greater than delta I2.
How? My
Because sir, because
P1,
sir, we know
my P1 is equals to P2. And in both cases, I am keeping my power same.
yes. So sir, we know that sir, wavelength. If I increase the wavelength, if we maintain the power,
Sir, delta ion equal to 2 delta I 2 delta I on.
No, it will be opposite. Delta I2 will be greater than delta I1 because the responsivity for my R2 will be greater than R1. So, because responsivity is increasing with wavelength. So, the wavelength for 1000 nanometer is higher wavelength. So, R2 will be greater than R1. So, my delta I2 will be greater than delta I1.
then is there any? I understand what you want to say there, but is there any particular relation is there?
Yes, there is a relation. So, it is after a few questions, I will come to that.
Okay, sir. Okay, no issue, sir.
What is bandwidth in context of photoreactors? The range of wavelengths that can be reacted, the maximum current output, the speed at which the reactor can respond to light modulation, the physical size of the reaction area.
Can I guess, sir?
Yes,
I think the speed at which the detector can respond up to light modulation.
that is correct. So let's say this is my light signal and suddenly I shine light on it. I will see that my light increases here. Then I turn off my light, it will again go like this. Then I shine again, this is how it will happen. So this is light on, this is light off. But there is a from going from light off to light on, it will take certain time. And then going back to light off, it will again take certain time. So if I shine my light, if I turn my light on and off faster, then I won't be able to reach my off state and on state completely. So like it will be like this. So there is a limit on how fast I can change my light on and off. And that is given, that is what which say bandwidth. So I want a clear distinction between on signal and off signal, but I also want to faster on and off. What is the rise time of a photoreactor? Time to reach
Time
maximum
from time from 10% to 90% of the peak photo current.
Time to reach maximum possible current, time between light pulses, time from 10% to 90% of peak photocurrent, time for complete signal decay. So you are correct. Time from 10% to 90% of peak photocurrent. So like I was showing, so this is my off current. Suddenly I turn on my light. So it will go like this. This is my I off. and this is my ion. And so this is 90% of ion, and this is 10% of ion. So the time I am taking going from this point to this point. So this is my delta t, which is my rise time. Similarly, for fall time, if this is my case, then the time between here to here is my fall time. This is what rise time, and this is fall time. And we want them to be as low as possible to have higher bandwidth. What is internal quantum efficiency? Ratio of output electrons to input photons reaching the active region, total power conversion efficiency, ratio of dark current to photocurrent, measure of optical absorption.
Sir, as for you say that in quantum efficiency means that if I apply 10 photons and you have got 10 electron pair, then it will be 100% quantum efficiency. So that the ratio of the output electron to the input photon reaching to the active region.
That is correct. So ratio of the quantum internal quantum efficiency is ratio of output photons to input photons reaching the active region. Basically, the active region is basically the region where your photon can be absorbed to generate electron hole pairs. That is basically your device region. But before your photons can reach your device region, there can be other processes involved, because your device is not just your photons, right? There will be some layer on top of it, like some glass layer or other things that are on top of it, that will affect our efficiency, and that is why we call it external quantum efficiency. So what limits the external quantum efficiency compared to internal quantum efficiency?
Yes, sir.
Temperature effects, applied voltage, collection and transmission losses, carrier mobility.
Sir, sorry for interruption, sir.
Yes.
Can you one more time say that external quantum difference between external and internal quantum efficiency?
Yeah, I will explain answer this question. I will explain through
No,
this
no, no,
question.
no, sir. Whatever you told that due to glass and other material, the efficiency will be less.
Yes. So the answer to this is collection and transmission losses. So this is, let's say, my device. This is my P region. This is my N region. There is some depletion region between. Here I am taking the output from P region. Here I am taking output from N region. These are my electrical leads. But in a physics, so this is fine. But in actuality, there will be some encapsulation, right? So it will be covered in some material so that it is not exposed to environment, right?
Yes, sir.
So when you shine light on this, so before it reaches this region, it has to go through this region, right? So there will be there will be loss when it travels through this region. And then here also it will reflect. It won't be completely absorbed, right? It will also reflect back from the surface. And So that is what your external quantum efficiency is. So it is a more realistic term. External quantum efficiency is a more realistic term compared to internal quantum efficiency. Because internal quantum efficiency only talks about this region, your active region, your main device, but the whole package that you have, because in real world you won't be using a bare device, right? You will be using a packaged device in the real world. So in real world terms, we talk about external quantum efficiency. Why might silicon not be active for selective UV detection? Silicon cannot absorb UV light. Silicon's band gap is too large. Silicon absorbs all wavelength above its band gap. Silicon degrades under UV exposure.
Well, P, sir.
The correct answer is silicon absorbs all wavelength above its band gap. So you so so UV, it will absorb all the UV radiation. So you won't be able to get a selective UV radiation. Like if I want to differentiate between 300 nanometers and 400 nanometers, I won't be able to do that in silicon. For that, I need a material which has a band gap between 300 and 400 nanometer, so that it absorbs 300 nanometer, but it does not absorb 400 nanometer.
Sir, can you explain one more time, sir?
Yes, so let's say I want a detector for 350 nanometer UV radiation, right?
Yes, sir.
So if I want it, but so if I shine a 400 nanometer light, it should not absorb. If I'm
Yes, sir.
shining 350 nanometer light, it absorbs, it gives me a signal. But if I'm shining a 400 nanometer light, it should not give me a signal. That won't be possible with silicon, because silicon will absorb both 350 and both 400 nanometer light.
So, sir, if we absorb both the lights, sir,
Yes.
so it can uh, means select the entire region, no, sir.
It is not selecting, right? How is it selecting? It is giving me light for every part, but selection is basically I want to select a particular wavelength. If I
Okay.
want to select 350 nanometers, but I'm also getting signal at 400 nanometers, then I'm not able to differentiate between both of them lights, right?
Okay. Sir, as per your concept, sir, if I absorb entire range, how can I isolate that this is UV region, this is IR region, and this is visible light region?
Yeah, you can say that way also.
Okay, sir. Okay. Sir, all wavelength above the band gap, sir,
Yes,
means that if the band gap will be 1.1,
yes,
so below all the range, it can absorb.
yeah. So like uh, basically energy above 1.1 it can absorb. Like
Energy, because energy is inversely proportional to lambda.
yes, so the
Okay.
wording is confusing, but basically it's energy above band gap and wavelength below the band gap wavelength. Like below 11, let's say 1000, let's say 1100, below 1100 nanometer. All wavelengths around below 1100 nanometer it can absorb.
Okay, sir. Okay. So below 1100 nanometer, it can absorb. and for below 11 nanometer it can absorb, and for wavelength it will be beyond 1.1 eV.
Yeah, in terms of energy, it is above 1.1 eV.
Okay, sir. Okay.
For 1 Gbps data transmission in fiber optics, what must be the photodetector be able to do? Detect 10.9 photons per second, generate 10.9 electron hole pairs, respond to 10.9 on-off transitions per second, operates at 10.9 volts.
The response to 10 to the power 9 on-off transition per second.
That is correct. So,
Because sir, you say that sir, to turn on and off faster, we get higher number of bits are detected, sir.
yes. So, basically 1 Gbps data transmission means that for every second I am sending in one 10.9 ones and zeros. So if my so if my light off is 0 and light on is 1, I should be able to there should be able to enough differentiation to get to say that this is 0 and this is 1. So I should be able to have more than my response speed should be higher than 10.9 per second. So what is the theoretical responsibility formula for 100% efficiency? Hc by q lambda, q lambda by hc, q by hc by q. So
HC by Q lambda,
it will be q lambda by hc.
Q lambda is equal to.
See, what I told you, responsibility is delta I by p, right? So you can write delta I as my n q by t. Delta you can write as n q by t. N is the number of electron hole pairs generated. Q is my uh, charge of an electron as t is time per second, let's say. And p I can write as my n ep e photon by t. N is this is, let's say, n e number of electron hole pairs generated, and this is np number of photons in number of incident photons. So and e photon you can write this as hc by lambda, correct?
Yes, sir. Yes, sir.
So now if I divide this with, I will get n e by np into, and there will be, so n with np I will also, so this will also be so then neq, my t will cancel with this t, so it will be ne, the lambda will go up, and I will have hc below. So this is q lambda by hc, and this is ne by np, which is number of electron hole pairs, number of output electrons divided by number of incident photons, and that is given, that is called my efficiency. So my responsibility formula then becomes efficiency into q lambda by Hc. Got
Sir,
it?
sir, first you write that R equal to del I by P in, then sir, del I you change that electron hole pair generated into Q by T.
Yes.
Then sir,
Because my change in current will be the number of output, number of electron hole pairs generated, right?
yes sir,
So that, and Q is my basically the charge of a single
charge.
electron.
Okay sir, okay.
So this is Ne Q by T, and my power is given by number of incident photons into energy of each photon divided by T. And then energy of photon I am writing as Hc by lambda. So
Okay.
I am cancelling T with T. So numerator will then be NeQ. This lambda will go up. So it will be NeQ lambda. And below I will have NpHc. And Ne by Np I can write it as efficiency. This is my external quantum efficiency. So my responsibility formula becomes efficiency into Q lambda by Hc. This is basic. This is eta. Eta efficiency is written by eta. So the question asks what for 100% efficiency. So my eta is 1 here. So my responsibility then is QHC by Q lambda by Hc, which is this. Got it? So now, what is noise equivalent power in photodetectors? The maximum power output of a device, the minimum output input optical input power at which signal to noise ratio becomes 1, the total noise generated by the device, the power consumed during operation. So what do you think is the answer? So the answer to this is the minimum optical input power at which signal to noise ratio becomes 1. So basically there will be some noise in your circuit, right? So, and when you're shining light, you will get some signal which is above that noise. But if you keep reducing your input power, your signal, your change in signal will reduce. And at some power, you won't be able to distinguish your signal from your noise. So that is called your signal to noise ratio has become 1 or less than 1 at that point. So that is your minimum that is minimum power at which you are not able to detect any signal. That is called a noise equivalent power.
Sir, explain one more time. I cannot get it.
Yes, so when my signal, let's say I'm not shining any light, I'm getting some random electrical signal like this. So there is electrical signal and there is some noise in it. And when I'm shining
Input,
light, it will go up and there will be noise like this in the signal. So I'm able to get a difference between this and this. But for some power, this will be my signal in off case and this will be my signal in on case. And here also, like I may be able to detect the change. But for some even smaller power, I won't be able to get any. I won't be able to detect between off condition and on condition. So at
Yes,
this,
sir.
so this is the minimum power at which I am not able to detect any signal. That is called my noise equivalent power, NEP. And then detectivity, D, D or D is 1 upon NEP.
What is the full form of D, sir? Detectivity.
Detectivity.
Okay, sir. Okay.
What is the main advantage of a PIN photodiode over a regular PN junction photodiode? Higher quantum efficiency, lower cost, fixed depletion width independent of bias, faster response time.
Sir, is this higher quantum efficiency?
The answer is faster response time. So a PIN photodiode basically means there's a P junction, then in the middle there's an intrinsic junction, then in the end there's a N junction. So if I have to draw like photo for a PN junction, this is my how the band diagram looks. But for a PIN junction, the band diagram looks something like this. So this is the P layer, this is the I layer, and this is the N layer, intrinsic layer. So for a PIN photodiode, I have my response time is faster.
Why, sir?
It will have a smaller depletion region, I think, and the diffusion length will be greater in the. I don't
What's the
exactly
length you move, sir?
what.
The total length of the total entire device will be more, no?
No, you can make a smaller also. That
Okay,
is
okay, okay.
does not matter. But
Sir, is this reason, sir, that for slope will be less, sir?
yeah, slope will be less in PIN diode. The depletion width will be smaller. So
Okay.
why are mid IR detectors often cooled to very low temperatures? To increase their speed, to reduce dark current and noise, to improve quantum efficiency, to extend their wavelength range.
Improve quantum efficiency.
To reduce dark current and noise. So you know the heat radiation is often given in the IR region, right? So
What, sir? What, sir?
the heat radiation in the environment is in the IR region, right?
Yes, sir.
So the so for an IR detector, mid IR detector, the because of the all the heat radiation around, the dark current will be much higher, and the noise
Okay.
also will be much higher.
Okay.
So if you cool it to very low temperature, then the heat radiation will reduce, and so it will you will able to reduce dark current and noise. So your detectivity will then increase. Then you will be able to increase your detectivity.
Okay, sir.
What is the main advantage of operating a photodetector in reverse bias? Lower power consumption, higher quantum efficiency, increased depletion width and reduced capacitance, better thermal stability, temperature stability.
Sir, increase deflection with reduced capacitance.
That is correct. So generally we operate a photodetector in the reverse bias region. So like I was showing,
Hmm? Okay, okay, okay.
this is your first quadrant, this is your second quadrant.
Yes.
This is your third quadrant, and this is your fourth quadrant.
Yes.
This is IV, I into V. So your LEDs operate in the first quadrant region. So you give a positive voltage, and you get your light emission. Your photoreactors generally work in this region, reverse bias region, and your solar cells generally work in fourth regions, because here you are talking about output power. So what we do is we take a negative of my uh, what I take is I consider my current to be negative, because here I am not giving power to the circuit, I am getting output power from the circuit. So I say that my current is negative.
Okay, sir.
So that is the questions I have for today. Thank you.
Sir,
Yes.
uh, can you explain one more time 26 equations, sir? 26 question equation.
Yes, sir.
Just, just only, sir. R equal to del I by P
Yes.
and equal to NEQ by T
Yes. So
equal to,
your current, what is your current? Charge upon time, right?
yes, sir. Yes, sir.
Yeah. So what is your, so what means what will your delta I? That is change in your charge upon time. So what will the change in your charge? That is the number of, that is the charge generated by the electron hole pairs, right?
Yes, sir.
So that is given by your NEQ. Q is your charge on single electron, and Ne is the number of output electrons, extra electrons.
Okay.
And Pn is given as your input power. So which is number of input electrons into energy of each electron divided by
Okay.
time.
Fine.
Because
Okay.
power, not power is
Okay,
energy
sir. Okay.
upon
Okay.
time.
Okay, sir.
So that is number of photons into energy of each photon. And energy of each photon I am writing as hc by lambda.
Okay.
So then my P in becomes NP hc
By lambda.
by T lambda.
Yes, sir.
So this T I can cancel with this T. The T from numerator I can cancel the T from denominator, right?
Okay. Okay. Okay, sir. Okay.
And when I, so then it becomes
Eta
N
into Q lambda by HC.
NEQ divided by NEHC by lambda.
Okay, sir.
And this lambda then I can take in the numerator.
Okay.
So that becomes this formula then.
Okay, sir. Okay. Thank you, sir. Should you give your mail ID, sir?
Uh, Let me write in the chat. So I have written it in the chat.
Okay, sir. Okay. Sir,
Yes.
if I have got some, not I, sir, all of got some difficulties, sir. If I mail you, sir, if possible, sir.
Yes, you can mail you can mail on my email ID or so. On I think on second, the I think on second, the Digbura sir is also taking a online class.
Yes, sir. Yes, sir. Yes, sir.
You
On
can.
that day you present, sir. You present, sir.
I don't think I will be there, but you can ask him your doubts.
Okay, sir. Okay. Okay, sir. Thank you, sir.
Thank you.